Have you ever just stopped and wondered how a single plain beam of white light can suddenly burst into a spectacular rainbow? It's one of those beautiful little mysteries that happens all around us. Well, today we're going to pull back the curtain and uncover the amazing physics behind this colorful show. So let's dive right in.
I mean, we've all seen it, right? Light hits a piece of glass or a diamond, and suddenly you've got this brilliant spectrum of color. You even see it in a drop of oil on a wet road. But how? What is the secret that lets plain old light make such an incredible transformation?
All right, to solve this colorful mystery, we have to start with our very first clue. It's a concept called refraction, and this is all about a simple, fundamental question: why does light bend in the first place? So, refraction, in the simplest terms, is the bending of light. It happens anytime light moves from one substance, like the air around us, into another, say a pool of water or a pane of glass. You know when you put a straw in a glass of water and it looks like it's broken at the surface? Yeah, that's refraction, right there in action. But here's the thing, light doesn't bend the same way through everything. Every material has this property called an index of refraction. You can almost think of it as a bending score. Water has one score, glass has a higher one, and diamonds, they have a really high score, which is exactly why they bend light so dramatically and give us that signature sparkle.
So, light bends. Got it. We've got that part down. But that doesn't explain the colors, does it? And that brings us to the big reveal of this whole explainer, a phenomenon called dispersion. This is the real secret behind the split. And this is the million-dollar question, isn't it? If a whole beam of white light goes into a prism and it all bends, shouldn't it just come out the other side as a bent beam of white light? Why on earth do we get a rainbow? There has to be something else going on here.
And here it is. This is the key that unlocks the entire puzzle. That index of refraction, that bending score we talked about, it's not actually one single number for a given material. It actually changes just a tiny little bit for each color of light, or, to get a little more scientific, for each wavelength.
So here's how it breaks down. Red light, with its long, lazy wavelength, actually travels a bit faster through the glass, so it gets bent the least. Then, all the way at the other end of the spectrum, you have violet light. It has a much shorter, more energetic wavelength, it travels slower, and it gets bent the most. Every other color, orange, yellow, green, blue, falls somewhere in between, each one bending at its own unique angle.
And this whole process has a name: dispersion. It is quite literally the separation of white light into all its component colors, all because each color bends by a slightly different amount. Now, the huge insight here is that the prism isn't creating the colors, it's just revealing the ones that were already mixed together inside that white light all along. And since the amount of bending is tied directly to the wavelength, the colors always spread out in the exact same order. It goes from violet, which bends the most, through indigo, blue, green, yellow, orange, all the way to red, which bends the least. VIBGYOR. It's a predictable and absolutely beautiful law of physics.
Okay, so now we get how light splits apart. Pretty cool, right? But let's take this out of the lab and see how this fundamental idea about light and color plays out in our everyday life, specifically in how we see things and how we mix colors.
So why is an apple red? Well, it's not because the apple itself is inherently red. It's because when white light, which contains all the colors, hits the apple's skin, that surface absorbs every single color except for red. It reflects the red light back out, and that's what our eyes pick up. Following that logic, a black object is something that absorbs all the colors, and a white object reflects them all. Now, this brings us to a super common point of confusion: mixing colors. Because it turns out there are two totally different ways it's done. When you're dealing with light, like on your TV or phone screen, that's called additive mixing. You start with blackness and you add colored lights together, the primary colors being red, green, and blue. But with paint or ink, it's subtractive mixing. You start with a white surface and you use pigments that subtract or absorb certain colors from the light that's reflecting off of it. Let's just focus on additive mixing for a sec. Now, this might seem totally backwards from what you learned with finger paints in school. If you shine a red light and a green light onto the same spot, you don't get some murky brown, you get bright, brilliant yellow. And if you mix all three primary colors of light, red, green, and blue, you get pure white light again. Okay, let's bring it all back home. We started this whole journey with a question about rainbows. And now, finally, we have all the tools we need, refraction and dispersion, to explain exactly how those magnificent arcs form in the sky.
You see, the real secret is that every single little raindrop in the air acts like a tiny, tiny prism. When a ray of sunlight enters the raindrop, it refracts and disperses, splitting into its colors. Then, those separated colors bounce off the inside-back wall of the raindrop. And finally, as the light exits the front of the drop, it refracts again, spreading those colors out even wider. So a rainbow isn't one single thing. It's the combined light from millions and millions of these tiny, natural prisms all working together. But believe it or not, the story doesn't end with the colors we can see. The beautiful rainbow that we perceive is actually just one tiny slice of a much, much bigger picture. So let's zoom out and take a look at the unseen spectrum. What we call light is really just one specific type of electromagnetic wave. The complete range of all these waves, from giant radio waves to tiny gamma rays, is called the electromagnetic spectrum. They're all fundamentally the same stuff, just vibrating at different wavelengths and carrying different amounts of energy. So it all starts with the longest wavelengths, which are radio waves. As the wavelengths get shorter and shorter, you move through microwaves that cook our food, then the infrared our remotes use, and then you hit that tiny, tiny sliver of visible light our eyes can actually detect. And it doesn't stop there. Beyond that, the wavelengths get even shorter and more powerful with ultraviolet, X-rays, and finally the highest energy gamma rays. Each one of these plays a critical role in our technology and our entire understanding of the universe. So let's just end with this thought. Everything we've talked about, from a shimmering rainbow to the color of an apple, is based on a tiny, almost insignificant fraction of the light that is constantly bombarding us from all directions. It really makes you wonder what unseen realities are flying right past us, right through us, every single second. If our eyes could see in microwaves or X-rays, what would the sky look like? What would our own hands look like? It's a pretty wild thought to leave you with.